104, we're going to talk about forces in action. We are constantly surrounded by forces. And we learned earlier in Module 1 that forces are simply pushes or pulls, which means we're exerting the force on an object. And we experience the force constantly of friction when a rolling object comes to a slow because we're pulling through grass or mud. There's also nuclear forces that keep atoms and molecules together, and those are what form all matter in the universe. And gravitational force keeps us on the ground and the moon in orbit around the Earth. We have four basic forces that physicists have uncovered between matter and gravity, electromagnetism, strong nuclear force, and weak nuclear force. The first two, gravity and electromagnetism, are forces we feel and experience every day. They also, because we feel them every day, means they are long-range forces. The other two, strong nuclear and weak nuclear, are shorter range forces. We'll talk more about that in a second. Let's move on to gravity. Gravity depends on two things, mass and distance. The greater the mass, the greater the gravitational pull. Let's think about a 300-pound person and a 30-pound person jumping on, let's put them on separate trampolines. And they're jumping. Who will get a larger jump on a trampoline, the 300-pound or the 30-pound? Of course, the 30-pound person can jump higher than our 300-pound person because they have less mass, which means they have less gravity exerted on them. And then distance. The greater the distance, the weaker the gravitational force upon them. So let's pretend, and only in your mind, please, not actually doing this. On the top of your roof, you jump off. The rate of your fall will be greater than jumping out of an airplane. So I went skydiving a few weeks ago, and I jumped out of a plane, and my rate of my fall is not as great as it would be if I jumped off my roof. Of course, there's a longer distance for me to fall, but how fast I was falling is slower up in a plane because I'm farther from the center of the Earth. So my distance matters on how much gravity is pulling me down. Gravity still pulls me because it's long range, but it's not pulling me as great with the distance. Electromagnetic force. This force interacts with electrically charged particles. I know you've heard opposites attract. This is totally true in the science of magnets. We know positive and negative attract to one another. They come and they pull in together. You ever had a magnet with a positive end and a negative end? Put positive and negative and they just pull your hands together. But if you try and put positive and positive together, you'll feel the force trying to push your hands away. They do not want to be together. So they are a force of attraction and repulsion. This, again, like I said, is a long-range force. And it affects everything that has an electrically charged particle. We have nuclear forces. We have strong and weak. Weak is exactly what it sounds like. It is a weak force, and nucleus. And then you see here nuclear, think of the nucleus. So inside the nucleus, what's happening is the nucleus is held together by a strong force. And the weak nuclear force means that it's decaying, or think of it as like falling apart. So it has to do with decay, radioactivity, and that's what happens when we have the weak nuclear force. The particles inside, which are the protons and neutrons, start to just kind of release out of the nucleus. And because it's a nuclear force, it has to do with the nucleus, it's a very short range. It's very unstable. Like I said, they're falling apart, so it's unstable. And it's very short range. Only has to do with the protons and neutrons inside the nucleus. Now, strong nuclear forces, just what it says, it is strong. This is what holds the protons and neutrons inside the nucleus. It holds it all together. And that's important because we just learned about the electromagnetic force, where the positive and positive will repel. Well, if you look in here, all of these plus signs are positives. The orange ones don't have a charge. They're neutral. So those positives are trying to push away from each other constantly. They want to get away from each other. The strong nuclear force is stronger than that and holds them all together inside the nucleus. So in the gamut from weakest to strongest, we have gravity as weakest, then we have weak nuclear, then electromagnetic, and then strong nuclear forces. So that's the range from weakest to strongest. And again, strong nuclear force is a very short range. It only has to do with the nucleus, so the protons and neutrons that are found in there. And you can watch this video on nuclear forces. I highly recommend watching it. It is definitely worth a watch. For 1.04, we're also going to do an awesome lab that I love doing. We're going to hang out with Galileo, and he's going to drop this large ball, small ball, and feather from the top of the Leaning Tower of Pisa. He's going to do it both in air and in the vacuum. So you need to make a hypothesis in the if-then format. So if this happens, then this will happen. So make your hypothesis. You're going to give Galileo the tools, and then you're going to push drop and see what happens. You're going to record 3 trials in air and then the 3 trials in the vacuum mode. At the end of that, you'll answer a few questions from the lab worksheet that is found here. Did the experiment support your hypothesis? Why or why not? I want to know more than just yes, it did. Tell me why or why it didn't. And what objects were, or what forces were acting on those objects when they dropped in the air and dropped in the vacuum. And then the part 2 is comparing and contrasting those 4 fundamental forces we just talked about: gravity, electromagnetic, weak nuclear, and strong nuclear. So you're going to choose 2 for the question 1 and choose the other 2 for question 2.